Hello. So in this lecture on the Legendre Polynomial chapter, we're going to introduce finally the Legendre polynomials because we still didn't talk about how we come up with polynomials coming from the Legendre equation. So just to refresh the memory, let's briefly summarize what we discussed last time. You can pause if you want at any time, so you can write this down. You don't have to write it down necessarily because it's on your notes. It should be on your notes from the last time, from the previous lecture. But let's summarize what we accomplished in the first lecture. We show that some boundary value problems, namely those in spherical coordinates, lead to Legendre equation. So leads to a Soloviev problem which can be reduced to this second order ODE in this form, also known as the Legendre equation. And we show that the general solution of this equation can be given by this linear combination of two functions in a series form. So we looked for solutions in the series form, and we show that we can find two different independent solutions in a series form, one of them containing even powers of x and the other one containing odd powers of x. Just to make it clear, this is essentially a convenient way to finding those independent solutions, because remember, we started with one series and we noticed that the coefficients of that series are given by recurrence of order 2. That means starting with one index, you can find the 1, 2 positions further, right? So if you know A naught, you can find A2. If you know A2, you can find A4, and so on. Furthermore, if I know A1, I can find A3. If I have A3, I can find A5 and all of the other odd coefficients. So that means as long as I can start with two different values for A0 and A1, then I can produce all the coefficients. But if alternatively I take A0 equals 0 first, AA and A1 not equal to 0, that gives me one solution, which is guaranteed to not overlap to the other solution when I choose, conversely, A1 to be 0 and A2 not equal to 0. So this recursion in two steps basically gives me this opportunity to basically come up with two different solutions that I'm sure they won't overlap. So that means they will be independent. Because remember, the general solution should be the linear combination of two independent solutions. So independently, both the one containing even powers and the one containing odd powers are solutions of the Legendre equation. Now, these are series, right? Power series, not polynomials. So that means these are infinite summations. How do we get to the polynomials, which are, remember, finite sums, similar to these, right? Powers of x, but finite summations. Well, this will basically, there is one remark we can make here, which will be connected, in fact, later on to the concept of the eigenvalues for a Sturm-Liouville problem in the Legendre equation format. For now, let's just notice that if lambda, this constant here, is of this form, so it's equal to the product of two consecutive natural numbers, then this recursion is guaranteed to stop. So, for example, notice that k starts from 0, 1, 2, and so on. And imagine, for instance, that you choose lambda to be 5 times 5 plus 1, which is basically 30, right? But purposely, I'm going to keep it in that format just to see that as k goes from 0, 1, 2, 3, and so on, as you come up with this iteration at each step, eventually, once k is equal to 5, then on the top of that recursion, you're going to have 0. Right? So you start with 0 for k, that's 0, 0 plus 1, minus lambda, which is 5 times 5 plus 1. So that gives you the next. And of course, in this case, you'll have to start actually with a1, because, again, this jumps 2 positions ahead, right? So I mean, if I start with 1, that means 1 times 2, it's the first expression here, minus lambda, and then it's going to be 3 times 4 minus lambda, and then eventually it's going to be 5 times 5 plus 1, and if lambda itself is 5 times 5 plus 1, then the numerator here will be 0. I'm going to illustrate immediately with an example. But again, once you choose lambda to be in the form of a product of 2 consecutive numbers, then depending, of course, on whether you start with a1 or a0, that will depend on whether lambda is positive or negative, you're guaranteed for this summation to stop, because you're going to have 0 on the numerator, and that means the next subsequent coefficient will be 0, right? It's going to be 0 times this, 0 times this, and so on and so forth. So this is what makes it a polynomial, and let's write it as a remark here, because that's the essence of constructing the so-called Legendre polynomials. So if lambda is equal to n times n plus 1, the series above become polynomials, and 2 types, right, containing even powers, if n is even, and odd powers, if n is odd. So the solutions of the Legendre equations can become polynomials once lambda is in this form that I just mentioned, n times n plus 1. So actually, let's illustrate briefly with a couple of examples how this summation stops, and then we're going to continue with some other properties of the Legendre polynomials. So let's do, I'm going to see, let's actually write again the recursion so we can have it in front of us. So the recursion that gives me the coefficients. And let's say I'm going to want to illustrate this with an even Legendre polynomial. So let's say I want lambda to be of the form 4 times 4 plus 1. Okay? And for this to stop, for this summation to stop, obviously I'm going to have to go through all the even coefficients. So I'm going to start with a0 not equal to 0 and a1 equal to 0. And that basically will give me an example of an even Legendre polynomial. So this will be an example of an even Legendre polynomial. Even degree, basically. And notice, for now, I'm not going to say what a0 is. There will be specific value for this for other reasons. I mean, because you have the freedom actually to choose any number you want here for a0. But let's actually illustrate how that summation stops eventually. So remember, k starts from 0, 1, 2, and so on. Now, of course, because a1 is 0, that means automatically all the even, all the odd coefficients will be 0. And then we just basically compute now the odd even coefficients. So first one, k is equal to 0. That gives me a2 equals 0 times 0 plus 1 minus 4 times 4 plus 1. I'm going to keep it like that for a moment just to illustrate how this summation stops eventually. And a0. And so now let's simplify. Minus 4 times 5 on the top, that's minus 20 over 2. So the next coefficient is going to be minus 10 a0. And next one is k is equal to 2. Remember, recursion is 2 steps ahead. So once I know a2, I plug in 2 for k, and I'm going to obtain a4. All right, move along. a4, if k is equal to 2, go back to the recursion. That's 2 times 2 plus 1 minus 4 times 4 plus 1. Right, that's lambda. That's fixed. Over, let's see, over 2 plus 1 times 2 plus 2, a2. And I'm going to replace a2 with minus 10 a0, right? So on the top now I have 2 times 3, which is 6, minus 20. 3 times 4, 12. A2 is minus 10 A naught. Let's clean it up a little bit. That's minus 14. That's 140 over 12 A naught. We can simplify that by 4. That gives me 35 over 3 A naught. And that's the next coefficient. And then the next one will be 0. So pay attention here. The next step on k equals 4, that'll give me A6. And when in k equals 4, that's the key thing, the numerator becomes 0, right? So k reached the value 4 and now matches lambda. So that's the whole idea, basically. As long as lambda matches one of these k times k plus 1s, then the summation basically stops. And this is A4. So I'm not going to even bother to plug in what A4 is, because on the top you have 0 over, 5 times 630, A4. That means it's 0. And automatically from this point on, 8, 8, A10, and so on, all of the rest of the coefficients, the even coefficients, will be 0 as well. So that means the 4th degree Legendre polynomial, which is basically denoted by P4 of x. So in the notation of these, when I write it down later, polynomials, Legendre polynomials, are denoted by P and the degree indicated on the bottom here as an index. And then, of course, the polynomial itself, in this case, will be A naught, the first term, then A2 x squared, which is minus 10 A naught x squared, plus 35 A naught over 3 x to the power 4. So Legendre polynomials either have even powers or odd powers, again, depending on the lambda that you choose. Let's illustrate another one when, let's see, with an odd one, odd degree polynomial. So suppose, for example, lambda is equal to 3 times 3 plus 1. This will have fewer steps. And for the summation to stop, this time around, I'm going to assume A not equals 0, which will imply immediately that all the even ones, all the even coefficients are 0, and A1 not equal to 0. So A1 is not equal to 0, so I'm going to have A3, the next point to determine here. If k is equal to 1, the next coefficient is A3. 1 times 1 plus 1 minus 3 times 3 plus 1 over 1 plus 1, 1 plus 2, A1. Sorry, it's out of frame. So 1 times 1 plus 1 minus 3 times 3 plus 1, 1 plus 1, 1 plus 2, A1. What does that give me? That gives me 2 minus 12 over 2 times 3, which is 6. Minus 10 over 6, A1. I can simplify by 2. That gives me minus 5 over 3, A1. And the next one will be 0, because notice A5, when we go back to the recursion, now k is equal to 3. It was 1 previously, now k is equal to 3. So on the top, I reach 0. And all A5 and the rest of them will be 0 as well. So that tells me let's write it here on the same page, the 3rd degree Legendre polynomial which is also denoted by P3 of x, is equal to A1x plus A3, which is minus 5 over 3 A1 x third, and that's it. Okay, so it's going to be of degree 3, containing only odd powers, obviously. So there's only 2 terms, because the only odd powers up to 3 are x to the power 1, x to the power 3. So at this point, before we move on to the second part, because we have to talk about some other properties, notice that I still didn't say how to choose, or if we should choose in some form, the starting point, A0 or A1. So remember, we can produce lots of solutions for the Legendre equation in the series format, as I mentioned before, provided that we start with different values, right? So I mean, you have basically the freedom to start with A0 or A1. The reason we start with 0 for A0 and alternatively with 0 for A1 is to produce 2 independent solutions, so automatically you end up with even powers or odd powers. And furthermore, if lambda happens to be of the form n times n plus 1, one of these 2 series becomes a polynomial. Okay, so if lambda equals 4 times 4 plus 1, you obtain a 4th degree polynomial with even powers. If lambda is equal to 3 times 3 plus 1, you're going to obtain 3rd degree polynomial which contains only odd powers, and so on. So nothing magic about this n times n plus 1, but keep that in mind, because to anticipate a little bit, that n times n plus 1 will be basically our eigenvalue, right? Because one of the things to obtain, I mean, one of the goals is to solve physical problems, so we need solutions which are continuous. So you can think of this choice for lambda as ensuring that the solution is continuous. Because if it's an infinite series, it might not be even convergent, but as long as it's a polynomial, then basically we are guaranteed to have a continuous solution, because polynomials are continuous at any point x. Now on the next part, I'm going to talk about how to choose these starting points, because again, you have the freedom to choose A0, you have the freedom to choose A1, but for practical purposes, there is a specific format for, a specific value one chooses for A0 and A1. Some of these values, how they are obtained, are given in the homework. And for practical purposes, there are some closed forms for these polynomials, so that you have a generic formula for a Legendre polynomial of degree n, because you don't want to basically go through this process one by one. You are better off to have a more compact formula for each Legendre polynomial. So more on that on the next part.